Hello students, welcome back. In this video we begin chapter 10, which has to do with correlation and regression. Section 1 has to do with correlation. So the key concept here is we introduce the linear correlation coefficient R, which we actually did back in stats 1. We said, does two sets of data have a relationship? Now, we didn't say, this is where we introduce the whole causation versus correlation concept, but the correlation just says that, hey, these two things are related. There is some kind of impact on one another, or at least as one goes up, the other goes up or down, or they definitely have some form of relationship in the way that the two-way frequency table can be graphed. So we are looking at linear meaning line, and we are going to be solving problems like that. So we are going to discuss methods for conducting hypothesis tests and to determine if two sets of data have a correlation to one another. So correlation, as you should know, exists when a correlation exists between two variables when the values of one variable are somehow associated with the values of the other. Linear correlation just means they go in a straight line or approximately a straight line when they are plotted. So this is a scatter plot. That's how we do it. Each one of these little dots represents a set of values for whatever your variable x and y are. And generally, the general trend is that these are going up. So that we would say that this is a positive linear correlation. And if you were to calculate this, R would equal 0.859. If you remember, R is a value between -1 and 1. A value closer to -1 or 1 would suggest a strong correlation. Values closer to 0 would represent no correlation. So if it's going positive, so up and to the right, that would be a positive correlation, and going down would be a negative correlation. As you can see, this is going down, -0.971. You would say that's a pretty strong correlation. There seems to be little that stray away from the general trend that is the line of best fit. This would be no correlation. The plots just seem very random, and thus an extremely small r, only 0.074, so very close to 0. And this would be a non-linear relationship. Something maybe like miles per gallon related to your speed. If you're going 0 miles an hour, you get bad fuel efficiency. Then maybe around, 60 miles an hour, you peak. And then once you go over that hump, the more miles per hour you go, the more the car has to compensate for wind resistance, so you actually get a fewer or a less fuel economy. That just might be an example of a non-linear relationship. This is just showing you what it looks like when it's graphed. So we measure the strength of the linear correlation with R. Again, this would be positive to the right. Now notice how this value suggests more of a relationship than this value, and that's shown by how much more closely together these dots are versus these dots. This is positive, negative, no correlation, nonlinear. So up to now, this should be review for you. So the linear correlation coefficient R measures the strength of the linear correlation. So what are we trying to do here? We are trying to determine whether there is a linear correlation between two variables. Do these have a linear correlation? Probably, but what if they were a little bit further apart? Okay, probably, but at what point do we say, no, sorry, that does not have a correlation anymore? We have to be able to calculate that, and we're going to do similar testing as we did in the previous chapters, now using the correlation coefficient R. All right, you guys excited? All right, cool. So let's go through some notation. So we have a small sample, only 4 pairs of data, 2, 3, 5, 7, with their outputs. So x is your input, your independent variable. Y is your dependent variable, your output. So n represents the number of pairs. So not the number of numbers, not 1, 2, 3, 4, 5, 6, 7, 8, not 8, but actually 4 pairs. So n is 4. This sigma right here represents the summation, so denotes addition of the items indicated. So if we said summation x, it would be the sum of all the x values. If we said summation x squared, it would be each x value is squared and then those values added together. And if we said the quantity sigma x squared, it would be add all the x values together and then square them. Note the difference between these two and their correspondingly different outputs as well. I'll give you a little hint. You won't actually have to do this part, but it's good to know where it comes from, because when you see the equation, you want to be able to know where the numbers come from. But I don't expect you or want you to do some of these complicated, convoluted equations with your calculator by hand. We want to just use a program in the calculator or StatCrunch. Okay? So sigma xy represents that each x value should first be multiplied by its corresponding y. R is the correlation coefficient for the sample population, and then P is the linear correlation coefficient for a population of paired data. So now we got the notation down. Let's go on to the next part. These are the requirements. I don't want to read these to you word for word, but must be good data. It's redundant to say that, but I guess you kind of have to cover yourself and say that the data needs to be good for you to do that. It should be common sense, but visual examination of the scatter plot should show that there is an approximate straight line pattern. And this next part's pretty important, not for the sake of checking the requirements, but just like kind of FYI, is that results are strongly affected by the presence of an outlier. A single outlier can totally throw off everything. So you should check for outliers first, and then remove any outliers before calculating R, because a single outlier, and I will show you this in the next section, a really good example, you can see that one outlier will ruin the entire calculation. So if you have raw data, check for an outlier first. Okay, here's your lovely, beautiful equation for how to calculate R. This is in your book as Formula 10.1. Looks pretty easy, right? Okay, here's Formula 10.2. A slightly easier one. 10.1 is what your any technology is going to be using. 10.2 is a simpler equation, and this is what you could use just so you can kind of see the general trends that R is going to have. It's a good format for understanding. Neither of these I will expect you to do. I expect you to be able to use technology by the end of this lecture PowerPoint. Okay. Just round R to 3 decimal places. That's another thing you need to know. Okay, so let's get into a little bit more of the meat and potatoes. So these are the new stuff. So we will use the p-value from technology to interpret R. So if the p-value is less than or equal to alpha, that supports the claim of a linear correlation. If the p-value is greater than alpha, does not support the claim. So kind of star this area over here. This is going to be something that you'll actually be using when we do these problems. Now, critical value R. You may remember this from when we did this back in Stats 1. Critical value R is the R value that we use to compare our calculated R when we are determining if there is a correlation. Now, that critical value R is related to the sample size n. So if you look in your book on table A6, it's on page 692. I have it in front of me. Not that you can see that, but page 692. And they have all the critical values for R. So that's what we're using to compare. So there is a correlation if the absolute value of our R that you calculate is greater than or less than the critical value, which you get from table A6. If the absolute value of R is less than the critical value that you get from A6, there is not sufficient evidence to support the claim of a linear correlation. I like this little graph. It kind of helps show that a little bit more. So you're going to calculate your R, and R is always going to be between -1 and 1. If your value is somewhere over here, you're in the correlation range. Your absolute value is going to be greater than this critical value R. And if you're in between the critical values, both negative and positive, there is no correlation. So one more time, you're going to calculate your R value using technology. Then you're going to use table A6 to determine what the critical R is. And then you're going to see which of these three ranges you are in. Correlation if you're over here and you're happy. You're unhappy and really sad if you're between them. Okay. Properties of the linear correlation coefficient R. Like I said before, the value of R is always, 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 always between -1 and 1. If you get a value that's beyond those limits, you did something wrong. Then you're sad. So the value of R is not affected by X or Y. What I mean by that is you have your two variables, whatever two things that you're comparing, whether it be miles per gallon of fuel efficiency versus how fast you're going, doesn't matter what you call X or what you call Y. So R measures the strength of the linear relationship. It is not designed to measure the strength of a relationship that is non-linear. We're talking only about linear. And R is very, very sensitive to outliers. So just make sure you don't have anything that's going to totally skew your data from one single point. All right, let's do a little example. I don't know why the book chose this example, but they are making the comparison between chocolate consumption and Nobel Prizes. Yeah, I don't know either. So chocolate consumption versus Nobel Prize. I guess it's like a per person, and then chocolate consumed per person versus Nobel Prizes per country. I don't know. Well, we're going to roll with it. So we have 5 paired data values. Use technology to find the value of the correlation coefficient R for this data. All right, I'm going to show you how to do this on your TI-84. So first you got to create 2 lists. So hit stat, enter, then you create your L1 and your L2 list, like I did over here. Exit out of that, hit second quit, or you can just go straight to step 2. So you can hit stat, go over to tests, go all the way down to F, where it says linear or linreg t test, like I show you on this screenshot over here. Then hit enter. Enter the data as follows. It might auto-populate for you because it kind of assumes that you want your lists to be L1 and L2. But if not, just populate it. Go over to calculate, where once that's highlighted, hit enter, and then you should get this. These are the same things. I just have to scroll down to give you the second screenshot. And we get an R value as shown over here, along with some other good stuff, which we will get to in a little bit. Right now, we are just calculating R. Okay, I'm also going to show you how to find R using StatCrunch. So enter the values for variable 1 and variable 2. Call chocolate variable 1, Nobel now variable 2. Then on the top, hit stat, go down to regression, simple linear. Let x variable be variable 1 and y variable be variable 2. Hit commute. So here is that shown, and you should get this value. Notice that our r's are going to be the same. And then you can see this graphed. Okay. Also on page 481 and 482 are step-by-step instructions for how to do it with several different technologies, and the value of R will be around 0.795. Okay. Let's just go through an example of where I calculated R using the complicated formula. Again, I don't want you to do this. Don't waste your brain capacity. You can even skip this part. Not that you would, because I know you love to hear my voice. But the point is that you're not expected to do this formula directly. You're going to be doing it indirectly with the technology. But you can create all your summations. So your sigma x, sigma y, sigma x squared, sigma y squared, sigma xy. Plug and chug. Boom. You get around the same R value. You can also use the formula using, I just showed you 2 formulas in the beginning, 10.1 and 10.2. That was 10.1. This is 10.2. So I'm going a little quickly for the same reason. La 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 la. Boom. There's your R value. Okay. Meat and potato example. Bringing it all together. So here is where this is the good example. Everything's building up to this. So we have 23 pairs of data. as shown on the next slide, we are going to use a significance level of 0.05. Here's the claim. Is there sufficient evidence to support a claim that there is a linear correlation between chocolate consumption and the number of Nobel Prizes? So here are your 23 data points. Again, I think that it's saying like this is the amount of chocolate consumed per person, and these are the number of Nobel Prizes, although I wouldn't know why there'd be decimals. Maybe it's like on a per capita basis of some sort. So, your requirement check, la la la, no outliers, random data, all good, so we're happy. Of course, you wouldn't go through that requirement check that quickly, but let's just move on. So, the real thing here is we're saying the p-value is less than or equal to alpha, supports the linear coefficient or linear correlation claim. P-value greater than alpha does not support it. So we're going to do the same steps that I did before, just trying to figure out that R value. So we have this data right here. I went into StatCrunch, and I have this chocolate being my variable 1, and then Nobel being variable 2. That's what I have over here. And then I went to the top, and I followed the steps like I showed you before, and this is my output right here. I have my R value, and I have my T values over here. Everything is done just that easily. It even gives you an equation, which we're going to get to, I think, next section. I think that's 10.2. But this is everything you're going to need for this section. Okay, here is it graphed. Okay, so the stat disk below, I did StatCrunch, shows the p-value is essentially 0. What does this show over here? The p-value is essentially less than 0.0001. Really, really, really small. So if the p is low, what does that mean? The null must go. So because the p-value is less than or equal to the significance level, we conclude that there is sufficient evidence to support the conclusion that for countries, there is a linear correlation between chocolate consumption and number of Nobel Prizes. Now, to show you that in another form, we are going to look at your table A6. So if you look at table A6, we have 23 data points. 23 data points with an alpha of 0.05. Well, it only counts by ones up until 20. So 23 is going to be between 20 and 25. So we know that our critical value R is going to be between 0.444 and 0.396. They interpolated. Your technology can also show you that value. So you get a critical value of 0.413. And you realize that it also represents the negative of that. Since our R value that we calculated was 0.801, I think I got 0.7998, so close enough. So since we are in this range over here, that suggests there is a correlation. I think this slide just says the same thing I just did. So we have a correlation. And although we found a correlation, I guess the point being is that because there's a correlation, just because there's a correlation does not mean that if you eat more chocolate, it will help you win a Nobel Prize. So this goes back to the whole correlation versus causation debacle. Okay, the next part is pretty interesting, I think, but I guess I also teach this for a living, so maybe that's not the best indication of if it's actually interesting, so you let me know. So, the value of R squared basically has a lot of significance. So it's the proportion of the variation in Y that is explained by the linear relationship between X and Y. All right, what does that mean? All right, so here's what it is. We have 23 pairs of chocolate Nobel data. We get an R of 0.801. What proportion of the variation in numbers can be explained by the variation in the consumption of chocolate? So all you have to do is you have to square R. So R squared is going to give you 0.642. So what does that mean? Here's my real kicker with this whole explain variation segment. So we conclude that around 64% of the variation in numbers of Nobel Prizes can be explained by the linear relationship between chocolate and number of Nobel I don't even know what this word is pronounced. I'm not even going to try. This implies that about 36%, the complement of 64, of the variation cannot be explained by rates of chocolate consumption. So if you R-square it, that tells you how much of the variation can be explained by the correlation. So once again, correlation does not imply causation. So common errors involving correlation, assuming that they directly affect one another as if it's cause and effect, and things like that. And okay, here's the last thing. I know this is a little bit of a longer section, but this is also important. So if we're doing a hypothesis test, if we are conducting a formal hypothesis test to determine whether there is a significant linear correlation between two variables, we use the following null and alternative hypothesis. Basically, the null, it has to involve the equal sign, so we will say that P equals 0. Remember that P is the linear correlation coefficient of the population. The alternative is that the P is not equal to 0. So this would be no correlation, this would be correlation. So if we're doing hypothesis test, we need to get a test statistic. So here is your formula for how to get the test statistic. However, the degrees of freedom is not n-1. Now it's n-2. Just keep that in mind. So let's do the same problem again. Now we're going to conduct a hypothesis test. So we have 0.05 significance level, and we are going to do the p-value method for testing the hypothesis claim. Okay. So we have our null hypothesis, which is that there's no correlation, and our alternative hypothesis, which there is a correlation. You can do this formula yourself directly, or you can use StatCrunch. Now this is actually the same screenshot that I did earlier in this slide. I hope it's not too far back. Right here. Back over this slide over here. This is where we got our t-stat, but we didn't really get to explain that part. So the same steps gives you your t-value. So once you get your t-value, your t-statistic, you know what to do with that. So technologies use more precision to obtain more accurate test values of 6.123. So with n-2 equals 21, table A3 shows that the test statistic of 6.123 yields a p-value that is less than 0.01. Or you can use StatCrunch to tell you what the p-value is. So because the p-value is less than 0.05, we reject the null hypothesis. If the p is low, the null must go. So we conclude that for countries, there is sufficient evidence to support the claim of a linear correlation between chocolate consumption and Nobel. So finally, you can also do this for one-tailed tests. Woohoo. All right, guys, that was section 10.1. Any questions? Shoot me an email.